conjugate complex roots. So now, say we got the auxiliary equation, we're trying to find the solutions to that quadratic equation, and instead of it being repeated roots, and instead of it being two distinct roots, we get imaginary roots or complex roots. If that's the case, and we have imaginary, so we do the quadratic equation, and you get alpha, which is going to be that a over 2, or negative b over 2a, and then we get plus or minus the square root of some negative number, so we have the I, so I beta. Those are going to be our two conjugate complex roots, a plus I times beta, or m sub 1 equals alpha plus b times I, or m sub 2 is going to be alpha minus b times I. Alright, so if this is the case, alright, we're just going to do the same thing that we did. We're going to have y equals our r, or our m value is going to be alpha plus bix. Now, one way that we can rewrite this is because it's addition in the exponent that can turn to multiplication. So we're just going to go ahead and do that. Or e to the alpha of x, that's going to be real. But we do have an imaginary part, e to the I bx. Or I'm sorry, beta x. So now, what we're going to do is we want to transform the way that this looks. And so what we're going to do is we're going to use Euler's equation. Where Euler's equation states that if I have e to the imaginary I times, something, so we'll say theta, that's just going to be equal to the cosine of that thing, so cosine theta plus I sine theta. Alright, so we're just going to use Euler's formula to rewrite what that looks like. So now, we're going to go ahead and say e to the I beta x is equal to cosine beta x plus I sine beta x. And that's all we did. Alright, so now what we're going to do is we're going to substitute this in for e to the I beta x. So we're just going to put that all the way right there. We're going to have e to the alpha x times e to the alpha of x. Go ahead and multiply. When we do that, we have a solution. E to the alpha x times cosine beta x plus e to the alpha x times sine beta x, and then we can put our c sub 1, c sub 2 there. So we have a solution. All right, now let's say we have e to the negative alpha minus beta I x. Well, it's the same thing. Y equals e to the alpha x times e to the negative beta x. We're going to change e to the negative beta x. So we're going to write that out. We're going to use Euler's formula. When we use Euler's formula, we're going to get negative beta x on the inside. Well, when you have it on the inside of cosine, because cosine is an even function, the negative is going to go away. When you have it inside of sine, though, that negative comes out in front because it's an odd function. So we get minus I sine beta x. And so now we can write that solution as e to the alpha x cosine beta x minus I sine beta x. Now, if we expanded this formula to make it look like this formula on the left-hand side, notice that e to the alpha x cosine beta x is going to be the same. And then instead of having plus, you have minus I sine beta x. Well, remember that minus I, it can be, it's a number. So even though it's imaginary, it's a number. That minus in front can be part of, a constant. And so they both hold true for the same type of solution. So even though it has minus I instead of plus I, because that's the constant part, we can say that's just going to be plus c sub 2 e to the alpha x sine beta x. And so there's our solution. Y, or our general solution. Y is equal to c sub 1 e to the alpha x times cosine beta x plus c sub 2 e to the alpha x sine beta x. So those are all the three different ways that we're going to be able to solve this, given, a differential equation of the second order. All right, or second.